Hello everyone, my name is Alexander Pombo, and today I'm going to talk about Scalaroca Stars, coupled scalar-Proca stars. First, what is a boson star? A boson star is an hypothetical astronomical object that is made out of bosons. You can imagine this as having a cotton cloud. And for these stars to exist, one needs a stable boson in nature. I would like to point out that the name of stars comes from the fact that these solutions have the size of a star, not because they fuse elements and emit light. For these stars to exist, these are compact objects. One usually needs a massive complex scalar field with a global U1 symmetry. These are everywhere regular lumps of scalar or vector bosons. So you can see these as solitons. They have been shown to be able to form dynamically and have been proposed as possible dark matter candidates. In this case, they will interact very weakly with electromagnetic radiation, but since these objects are very massive and compact enough, they will be able to create an accretion disk and even bend light around them. Now, let us talk about the model. The Einstein matter action for both the spin 0 and the spin 1 comes as follows, where the scalar field phi is the scalar field, and the Proca comes as A. In both cases, we consider an harmonic time dependence with a radial dependence that defines the amplitude. And these solutions have dispersiveness associated with the harmonic time dependence that is counterbalanced by the self-interaction potential that in this case is solely containing the mass term of each field. But now we have to add another parameter. But first, in the absence of the vector field, we have scalar boson stars. If we consider only the vector field, we have what are known as Proca stars. And then we can add the following coupling, a mass-like coupling. And depending on the sign, a value of alpha, we can have different objects. If alpha is equal to 0, we can have a superposition of scalar boson stars and Proca stars. And we call these as just superposition, since these stars only see themselves each other through gravity. Or we can have a non-negative, non-zero value of alpha. In this case, the fields interact between themselves, and we can have either a positive or a negative interaction. For the case of the positive interaction, we can have synchronized solutions. With this set, we are able to numerically integrate the set of field equations and obtain the following results. On the right plot, I show the domain of existence for superimposed stars, where we present the mass as a function of the effective frequency, which is just the average weight frequency of each field. And this domain of existence is delimited by the Proca star, which is at blue, and by the scalar boson star, which is at black. And we can see that all the Scalaroca stars continuously interpolate between the Proca star and the scalar boson star. One known result for these boson stars is that the stability goes from the maximum of the domain of existence spiral until the maximum of the frequency. And we can observe that there are some Scalaroca stars that start at an unstable Proca star and end at a stable scalar boson star, while the opposite never occurs. If we pick one solution at random, we can see on the left side the radial profile, and we see that it is regular everywhere. We can then add a positive coupling, alpha, and we see that for relatively small values of the coupling alpha, solutions are more or less the same as before. Solutions continuously connect between the Proca star and the scalar-boson star. However, for high enough values of alpha, we see different behavior. Solutions start from the scalar-boson star. It increases the vector field until a certain point. After this point, no more vector field is supported, and the solution stops. At this point, solutions are everywhere regular. However, there is a tachyonic mass for the vector field. And we expect that a strange phenomenon of self-spontaneous vectorization occurs. In this case, we have started from the Proca star and added a little bit of scalar-boson star, and we have observed that no amount of scalar field is supported by the Proca star in this case. For the positive coupling, we can also obtain synchronized solutions, which we can observe that they start from the Proca star and never go to the scalar-boson star. And in this case, we have a different behavior. While before, we never had solutions that are more massive than the Proca star or less massive than the scalar-boson star. Now we can have solutions for sufficiently high values of alpha. We can have solutions that are more massive than the Proca star, and then it's also more compact. This is something that we saw before for a small region of the space for the high enough values of alpha. We can see if we pick one solution at random, let's see the last point at alpha, the largest alpha, we see that solutions are everywhere regular. But at this point, the vector field amplitude at the origin goes to 0. And while it seems to be just a numerical problem, we are not able to further explore the domain of existence. That also seems to occur for everywhere. For the negative value of alpha, we observe the opposite behavior. First, solutions are everywhere regular. And for small, well, the inside of the domain of existence spiral, we see that solutions are as before. However, as we go outside, we see that now solutions start from the vector field. They have an increasing scalar field until they stop. After this point, no more solutions are able to obtain. And in this case, no tachyonic instability seems to exist. If we compare the negative alpha with the large positive alpha, we see that, again, the behavior is the opposite. While one starts at the scalar-boson star, the other starts at the vector-boson star. However, we see that there is a larger impact on the negative alpha than a positive alpha. In addition, these solutions also can endow solutions where the vector field frequency is able to sustain the entire Scalaroca star. This means that we can have solutions with a real scalar field. So the scalar field frequency goes to 0. And we see that in this case, solutions are everywhere regular again. At last, we have studied some phenomenology. We have studied the orbits around the Scalaroca stars, taking into account one of the latest Gaia measurements. And we can see that for all the observed solutions, parameters, the observations are well constrained. And this is easy to understand because the Scalaroca stars are more or less between 10 and 100 times the radius of a black hole. So for astrophysical observations, this is as if this is a black hole. We have also computed the inner time-like circular orbits, which gives the inner edge of the accretion disk, and also the light rings. And we observe that for the case of the light rings, no stable solution exists with light rings, but for inner time-like circular orbits, solution does exist. And this can be compared with some of our previous works. To conclude, in this work, we have studied simultaneously scalar boson stars and vector boson stars, and an object that connects between them, which we denominated by Scalaroca boson stars. These solutions are more compact and massive in some cases, and they can be made by real scalar fields. They can also yield this strange phenomenon of spontaneous self-scalarization or vectorization. With this, one can impose lower particle masses for the scalar and vector fields, probe extra interactions between these fields, and also observe that these solutions can be similar to black holes and orbits, all while verifying all astrophysical observations. Thank you.